We're building a new mixing and mastering studio and filming the entire process so you guys can follow along. This is video 2 in this series where I'll be talking about our goals and going through the design of the room. If you didn't catch the first video in the series where I went over the starting space before the build began, I'll link that below in the description. Heads up, this is going to be a super deep dive video. Prepare for a lot of notes. You might want to grab yourself a tea or a coffee, and actually forget the coffee. You probably want a glass of scotch for this one. Great, now that we got that sorted, let's hop into it. I have a previous studio that was built in a rental space. When we constructed the room, I knew we'd have to move out of it eventually, so the entire room was built using modules that could be easily removed and set up in a new space. Here are a couple shots of the previous room. The new space has much larger dimensions, as you can see by this comparison of footprint. My original room is on the right, and the new room is on the left. We're also working with much higher 10-foot 7-inch ceiling height versus the original room that had 8-foot ceilings. So the amount of treatment possible in the ceiling is greatly expanded. And I'll have to say the 8-foot ceiling height of the original room was the main limiting factor that we had in the design, and it was the only aspect of the frequency response that we weren't completely happy with in the room. When building a studio, it's really important to have clear goals and priorities. So this is built as an engineering control room. It is not a recording studio. It's not a creative studio with like instruments and MIDI controllers and all kinds of stuff all over the place. It doesn't have plants in the room like my room does here. And it is not intended for anything except hardcore engineering. So it's built with one goal in mind, which is optimal acoustics. This means it must have a very short decay time in the room. We aim for around 100 milliseconds across all audible frequencies. You can see this waterfall from my 2018 studio. This is a measurement from Room EQ Wizard, which was used for all the acoustic testing. It shows amplitude and frequency, then decay time in milliseconds on the Z plane. You can see that we achieved a very short 100 millisecond decay time right down to 80 hertz. But below that, we had some low frequency ringing that happened around 40 hertz and below, and it was about 500 milliseconds. That wasn't ideal, and it was because the studio was framed inside the family room of a residential house with limited ceiling height and not enough room for deeper porous absorption using low density material. This is not an issue we have in the new space. We have room for much deeper absorption, especially in the ceiling and on the back wall. Even with the super low frequency ringing, the acoustics in that room were far better than any room I'd worked in before. Here's a waterfall of the previous studio I was working in that just had prefabricated 2-inch and 3-inch panels and terrible room acoustics. It was a very small room. Unfortunately, this is what a lot of home studios look like before you put some serious attention into acoustics. You can see there's huge peaks and nulls from constructive and destructive interference from all of the out-of-phase room reflections. Plus, you have certain frequencies that are ringing out much longer than others, which gives you the impression as an engineer that they're louder. If you were mixing your low end in that room, you may end up EQing your track like this to achieve a balanced sound. But then you'd go to play it somewhere else, and your EQ moves would now be compensating for acoustic issues that don't exist in the new listening environment, and your track sounds rubbish. This is why so many people have issues getting their mixes to translate. It's actually their room acoustics getting them to chase ghosts while mixing. Let's get into the details of the design in the new studio now. My acoustician and studio designer is Tom from Storm Acoustic Design and Consulting. He designed and built our first room back in 2018, and now he's on site doing the build for this new room. Tom used to work for GIK and has designed over 300 studios around the world. He specializes in building control rooms for engineering bass heavy music, which is exactly what we do at Warp Academy. You don't often find people who have the design chops and the studio building expertise to handle a project like this, so it made complete sense to work with Tom. We're starting the build by creating an isolation shell. The room the studio is in is actually a garage, and we have an Airbnb suite that's adjacent to it, separated by a small workshop. The reason we're building an isolation shell is twofold. One, I live in Canada, and it's cold here. We're building the shell partially to up the R value of the space and thermally insulate it. Second, we have rental suites on the property, and then neighbors. So we need some isolation. Isolation keeps a higher proportion of the sound generated inside the room, like from your monitor speakers, from bleeding out and disturbing neighbors. This is also known as transmission loss. And it also keeps some of the sound from outside of the room, like maybe your neighbor's using a lawnmower, a truck driving by outside, someone starting their car. Keeps that stuff from bleeding in and interfering with your ability to hear what you're working on as an engineer, or if you're recording, from bleeding into your recording. Now, there's a common misconception that adding acoustic treatment to the inside of the room somehow prevents sound from bleeding out. This isn't quite the case. Interior acoustic treatment does help to attenuate the sound generated inside of the room, and it does do a bit of good for transmission loss, but a professional studio doesn't rely on that to prevent sound from bleeding out. They do the heavy lifting by adding mass to the boundaries, which has a much more prominent effect. You use multiple layers of high mass material, such as drywall, to create a hard boundary to minimize transmission loss, and that way you're not disturbing adjacent rooms and compromising recording or creating issues with neighbors. It's not uncommon to use 4 layers of drywall to create an isolation shell, but there is a significant downside to isolation. When you prevent sound from leaking out, it's now contained inside your room, bouncing around. Your room becomes much more reflective as mass is added to the boundaries, so the interior acoustics get worse as isolation improves. This means you need more acoustic treatment in a room with an isolation shell than in a room with standard lossy construction. An isolation shell also emphasizes your room modes, so as you increase isolation, you're also emphasizing the room modes. It's for this reason that we decided to maximize our room volume for this build, to leave plenty of space for additional treatment modules. As you can see from the old room to new room side by side, the amount of additional treatment in the room is massive. Additionally, the entire ceiling is going to be a huge porous absorber assembly with multiple layers. In our design, we went with 2 layers of drywall instead of more because we're actually okay with some transmission loss given our distance from our neighbors and the fact that there's a workshop in between the studio and the Airbnb suite. Using 2 layers of drywall instead of 4 gives us better acoustics inside the room because more of the base energy has a chance to escape. I want to speak to the dimensions of our isolation shell of the room. Some people have asked if we're using one of the golden ratios for room designs. No, we're not. Those golden ratios are designed to space out the room modes so they don't stack on top of each other, which makes them worse. That's more relevant in a reflective room. In our case, adding a high depth of treatment is our strategy, so maximizing the interior room dimensions within the garage took priority. Our room will not be very reflective at all, and the room modes will be highly damped, so a golden ratio in terms of our dimensions is not as relevant. Okay, let's talk about the floor. A lot of builders who don't specialize in studio construction will tell you to use floor joists with an assembly of framing lumber. It looks something like this. While that may work well for residential construction, it's not great for acoustics. What it does is creates a series of resonant chambers underneath your studio. You might think maybe stuffing them with rock wool or fiberglass sorts the issue out, but it actually doesn't. In our case, we went with a fully solid floor with EPS, then subfloor with OSB, and then laminate on top of that. This ups the R value a lot and also acts as a vapor barrier because we have concrete slab underneath us and it's not insulated and there's no vapor barrier underneath it, so moisture can leak up if you're not careful. In this image, you can also see the wall assembly with the 2 layers of drywall and then the isolation shell wall. The construction's been designed to be as airtight as possible with a sill gasket and then acoustic sealant. The front wall is where the magic really happens in this room. A high-mass, hard front wall will contain flush-mounted Neumann KH420 reference monitors that I just picked up. Building a hard front wall is complicated and expensive, so you might be asking yourself why go to all that trouble. This really could be its own in-depth video, but I'm going to point out some of the top benefits as succinctly as possible. Benefit number 1 is SBIR. I'm sure by now many of you have heard of speaker boundary interference response, or SBIR. It's basically when you get a reflection off of a room boundary, like a wall, the floor, or the ceiling, and it rejoins the direct monitor drive signal, but out of phase. This causes destructive and constructive interference that can dramatically change the frequency response of your room. I'm going to quote Arkin here. This is a site that's a great resource for understanding acoustics for control rooms. The only way to truly thwart SBIR is to flush mount your monitors in a hard, rigid wall. This is how main monitors, aka mains, are mounted in $1 million recording studio control rooms. If your studio monitor speakers are designed to be flush mounted, the best place for them is in your wall. Your speaker baffles flush with the wall surface. Your front wall becomes a giant speaker baffle, an infinite baffle. Proper flush mounting means no front wall reflection, and that means no speaker boundary interference response from your front wall. Your speakers will sing in harmony. Also, flush mounting increases acoustical loading, which helps drive your monitors, making them more efficient at low frequencies. It really is awesome. I'm also going to quote Philip Newell here, author of Recording Studio Design, because he has many references in his book In fact, it's the most referenced topic in his entire book in terms of talking about the front wall, and his explanations are really on point. In the top level control rooms, it is general practice to build the monitor loudspeakers into the front walls. So just take a look at this image and then compare it with my room design. You notice a lot of the similarities, and then look at the side profile of the room. See how much trapping there is in the ceiling. It's insane. This is why multi-million-dollar studios have huge ceiling height. We're talking like 4 meters. Okay, back to Philip here. If the loudspeaker is placed within the room, as opposed to being flush mounted within the boundary, it also sends low frequencies to the wall behind it, which then add to the reflections in the room. This rear radiation leads to a wave pattern that is much more complex in the room with freestanding loudspeakers than in a room in which they're flush mounted to the wall. So why is it only the base frequencies? It's because as frequencies get lower, the radiation of frequencies becomes more and more omnidirectional, unless you're talking about cardioid speakers, which are still fairly rare. So the mids and the treble is much more directional and it radiates forwards. But as you get down to the lower and lower frequencies, the bass end of the spectrum starts to radiate backwards from the speaker, irrespective of the speaker's directionality. So you get this bounce off the front wall, which then severely deteriorates your low end response. You also get an increase in efficiency in the loudspeaker, especially in the low end, because the sound can only travel forwards and it's completely in phase rather than backwards. So Philip states, if the pressure wave cannot travel behind the loudspeaker, all the pressure is concentrated in the forward direction. So the normal forward propagation is augmented by the would-be rear radiation. The effect is virtually instantaneous, and it's equal throughout the entire space into which it radiates, so that it can actually be considered a part of the loudspeaker response in those given conditions. A response modification of this nature is minimum phase. So let's take a look at one of the pages out of the book, Recording Studio Design, and we're going to take a look at the frequency response of a NS10M. Okay, so take a look at it when it's freestanding, and then take a look at what happens to it when it is flush mounted into a wall. You notice the improvement in low end response, and then you also notice a flattening of the response in general. And that's our target with this design. So just to try and put this in layman's terms and remove some of the academic lingo here, imagine that you and a friend are both standing up and you're pushing against each other. You're exerting force into each other's hands and you're trying to effectively push each other over, right? You're needing to brace against your back foot and lean in. But now imagine one of you is positioned so that you have your back up against a concrete wall and you're pushing forwards and you're able to exert much more force than your friend who is freestanding. So it's kind of like a loose example of kind of what we mean here with the effect of putting the speaker in the wall and increasing the loading. So this results in a measurable response increase in the low end, which is known as baffle step. So in some monitor systems, it's actually advantageous to have this lift in low end, but in other monitor systems where it doesn't actually need that low lift, now you have too much LF in the room, but it's a easy to solve problem because you can just use the EQ dip switches at the back of the monitor. Most monitors have shelving filters, and you can shelve down to account for that increase in low frequency. Benefit number 2 is that it increases the distance from the monitors to the mix position. So I'll quote Philip Newell here again. No studio for music recording can seriously call itself professional unless it has adequate full range monitoring. Relying on small monitors that roll off rapidly below 60 Hertz is not a professional approach. This is why I chose the Neumann KH420s here. They are large 3-way monitors. They have incredible low frequency response all the way down below 30 Hertz, and they're a full range midfield monitoring system. However, due to the physics of electroacoustics, loudspeakers which go down to 25 Hertz or thereabouts, and which can produce adequate sound pressure levels, tend to be relatively large. In a small room, large loudspeakers at short distances tend not to have flat responses, and the response tends to change with small movements of the head, which can be misleading. In small rooms, it's advisable to flush mount the loudspeakers in the front wall of the room. This puts them at points of maximum distance from the listening position. Flush mounting is the only realistic option for high-quality monitoring other than in free-field anechoic conditions. Otherwise, a maximally flat response cannot be achieved. Benefit number 3 is that it improves stereo imaging. In Recording Studio Design, Philip Newell states, the sharp edges of loudspeaker boxes, mixing console meter bridges, and any other abrupt cross-sectional changes between loudspeakers, and the listener will form secondary diffraction sources that can smear a stereo image. So this is edge diffraction. This is why you don't want a huge mixing console in front of you if you can avoid it, or a desk with tons of equipment on it in the way. This is why you see a lot of speaker cabinet designs that have been beveled or rounded, like in the Dynaudio cabinets or in Genelec MDE cabinets. MDE stands for minimum diffraction enclosure. So what Philip says about this is the expanding wave, like a wave generated by a tweeter, for example, travels along the front surface of the loudspeaker cabinet until it arrives at a discontinuity, such as the cabinet edge. From this point on, it suddenly has to expand more rapidly around the corner, but the same pressure can't be sustained in the new larger volume into which it expands. This sudden increase in the expansion rate is due to the change in acoustic impedance, and any change in impedance will send back a reflected wave. So sound radiates from that point. Objects in any room in which a loudspeaker may be positioned, and especially objects close to the loudspeaker, such as mixing consoles on which they may be mounted, can all act as diffraction sources. So in our application, the large front wall that's flush with the front baffle of the monitor speakers acts as an extension to the baffle. So it enlarges the baffle, which means that you're not getting edge diffraction from the edges of the monitor speaker cabinets. Now, the sound wave still travels down until it reaches the edge of the baffle, but at that point we have substantial treatment that is intended to catch that. It doesn't necessarily mean that you completely eliminate diffraction, but you have a far superior stereo image and phantom center and sense of soundstage in a room with these flush-mounted monitors in a large front wall. Benefit number 4 is that you have a dramatically improved transient response with flush mounting. Let's take a look at this image. At the top, you see a really nice, clean transient. This is the way it would appear at the source in the recording. And then we have the bottom one that's been destroyed by the manipulation of the phases of the component frequencies, so such as the harmonics in relation to the fundamental and harmonics in relation to each other. So when you have your speakers inside a room and then you have reflective surfaces, the walls, the floor, the ceiling, sidewalls, and they're all at different distances from the speaker, which is obviously the case, you create all of these out-of-phase reflections. Furthermore, the relative phases of each frequency will be different. So this creates that transient smearing effect that you can clearly see. By putting the speakers in the wall, you solve a large part of that problem by eliminating the front wall SBIR. Then by treating the ceiling, sidewalls, and back wall, you absorb and attenuate the other reflections. Now you still have a hard floor, and there is a pronounced floor bounce, but we'll block that largely by locating the desk in the reflection path. Our fifth and final advantage is the fact that you have a live surface in the room. So when you're mixing in a room that is completely dead, like we're talking anechoic chamber here, your brain is quite likely to freak out. They've had lots of examples of that when people go into anechoic chambers. They'll freak out after a very short period of time because you don't have any of the natural acoustic feedback from surfaces around you that our brains find comforting and natural. So in really nicely dialed control rooms, they are highly damped, they're highly absorptive, but they still have some feedback from the room to allow the engineer in the room to feel that natural sense of reflection. And the front wall is the perfect place to do that. All right, let's talk about acoustic treatment now. So the goal is to create a reflection-free zone, or an RFZ, in the mix position that will completely, effectively eliminate any early reflections that can smear the stereo image or interfere with the direct sound from the monitors. In our design, we have between 1 and 3 feet of treatment in all areas of the room except for the floor and the front wall. When going deeper like this with your treatment, you have to be very careful about the density of the material you use. Many of you will have heard to use OC 703, which is a rigid fiberglass density insulation product, super common in acoustic panels, especially ones that predate rock wool, or many of you will have been told to use rock wool. Now, these products come in a whole bunch of different densities. So say you're only doing a 3-inch thick panel, that's a common depth for a lot of prefabricated stuff. You could use higher density material, but the thicker you go, that'll start to work against you. Each material, rock wool included, can become increasingly reflective the thicker it gets. Yep, that's right, I said reflective. You wouldn't necessarily think that porous absorption is going to become reflective, but if you use, say, 2 feet of rock wool, it'll actually start reflecting sound back into your room, thus partially defeating the purpose of the thicker absorption. So What you want to do is use material that's the correct density for its depth. The density that you choose will be relative to the thickness of the treatment. The cool thing is that when you're paying for porous absorption, like rock wool or fiberglass, you're paying for the weight of the material. So to use more low density material or less high density material will often be very close to the same price. Now, this leads to another important question that I know a lot of you will have, and that's, are we air gapping behind the modules, behind the absorption? So in some cases we are, and in some cases we aren't. The effectiveness of air gapping is very design and situation dependent, and we're using a mix of both. Now let's talk about the rear wall. In the back of the room, we have rear modules with wooden slats on them. The slats provide a bit of scattering in the upper frequencies, which helps the room not to sound totally dead. These slats have been cut at different thicknesses using a formula and attached to the rear thick absorption modules in the back end so that there's a reflective wooden surface alternating with an absorptive surface. The rear modules also have nice CNC panels that have the Warp Academy logo on them, and they're backlit with LEDs to add some color and vibe into the room. All right, there we have it. See why I said to grab a glass of scotch for that one? I hope your brain isn't feeling melted. It's a lot of detail there, but I really wanted to share, when you're going and learning about building studios, which I've been learning about studios and acoustics for years, you just encounter so much misinformation and pseudoscience out there. And I've really had a great time and benefited a lot by working with a stone cold professional like Tom. And I wanted to take a lot of what I've learned from him and what I've learned just through my own study. I've been avidly studying acoustics for years now, and share that with you guys. Hopefully, some of this information will prevent you guys from making some of the common mistakes that a lot of DIY studio builders will make, or maybe it'll inspire you to up your game with your own studio and start investing into some acoustics. In either case, I hope you found this video useful and informative, and I would love to catch you on the next one. So this is only video 2 in the series. I'll be posting updates soon. And stay tuned. I'll catch you on the next one. Peace.